Okay, so in the last video we talked about the two-slit experiment, and we said that in order to understand the wave-like behavior of electrons in this experiment, we should consider the state of the electron as defined in terms of this wave function, which is a function I called A, which depends upon position and time, and also that the probability to detect the electron at a particular point, x and t, should be equal to the absolute value of this wave function squared. Okay. So what I want to do in this lecture is talk more about this wave function and how it behaves, and in particular we're going to see the connection to the Heisenberg Uncertainty Principle, which you may have heard of before, and also the relationship of this function to the de Broglie wavelength of the electrons. Okay, so we'll start then by talking about the de Broglie wavelength. Okay, so remember, what is the de Broglie wavelength? This is saying that to any particle we can define a wavelength lambda in terms of its momentum, just h divided by p. So rather than talking about a wavelength lambda, often you can also talk in terms of a wave vector k, which is defined as 2 pi divided by lambda, and we will use this in the description in terms of the wave function. So a wave function which is a pure plane wave of this form, okay, where here a is a constant, no longer a function of x. This is a wave function with momentum given exactly by the de Broglie formula there. So p is equal to h over lambda, okay, but here this k is the wave vector, so lambda from this formula is equal to 2 pi over k, so this is equal to h over 2 pi over k, which is equal to h over 2 pi times k, and hopefully you remember h over 2 pi was the definition of this reduced Planck constant, h bar. Okay. So this shows the relationship between the de Broglie wavelength given by this formula here and a particular wave function. So if we define a wave function which is just a plane wave with wavelength given by lambda, then the momentum of the particle described by this wave function is exactly that given by the de Broglie formula. Okay. But now we have to consider what happens if this function a is not a constant. Okay, so in other words, the wave function is not simply a plane wave. Okay, so an example which is often useful to think about is what's known as a wavelet. So this is a kind of wave with a well-defined, which exists within a well-defined region of space. Okay, so what does that look like? So if I were to draw that as a function of x, then rather than a plane wave, you have a plane wave here, but as you move away from a particular point, the amplitude of the plane wave drops down to 0, like this. Okay, so in the region here, the wave looks like a plane wave, but outside of this region, the amplitude drops to 0, usually with some exponential decay. Okay, so this orange line here is what's defining capital A of x, okay, and we take the wave function axt to be this envelope, capital AX, times the plane wave. Okay. Then, in this case, we can describe the wave function axt in terms of its Fourier transform, but its Fourier transform, because it's no longer a plane wave, will have a range of possible k values. Okay, so what I mean by that in terms of a picture is if we take this original wavelet here, then we can say that this is equal to, firstly, a plane wave which has exactly the same wavelength as the original wave here. So we try and get it about the same. Like this, okay. But you add on to this waves of slightly greater and lesser frequencies. So this is one with a slightly greater wavelength, and one with a slightly lesser wavelength. This, okay, and by adding together a series of these plane waves, you can get a wavelet which looks exactly like this. Okay, but here, each of these plane waves here in the Fourier transform will have slightly different momentum. So if this one has a momentum p given by the de Broglie formula, then here, because the wavelength is bigger, that will mean that the momentum is less. And here, because the wavelength is less, that will mean that the momentum is more. Okay. And what this means is this wavelet introduces an uncertainty in the momentum of the particle. You cannot say exactly what the de Broglie wavelength of this wave function is, and this introduces uncertainty in the particle momentum. Okay, so we can quantify this uncertainty as a statistical measure in terms of the standard deviation of momentum measurements, and then that gives us a numerical measure for the uncertainty in momentum measurement. Okay, so to actually calculate what this uncertainty is requires taking the Fourier transform and so on, so I won't do that, but you will definitely see this in a quantum mechanics class. And note that such a wavelet also has uncertainty in the position of the electron. Remember, the orange line here is related to the probability of detecting the electron. So you're more likely to detect the electron in the center of the wavelet here than you are at the edges here and there. Okay. Okay, so again we can mathematically describe this by some standard deviation in the position measurements, which we can call sigma x, and then this leads to the Heisenberg Uncertainty Principle, which says no matter what wave function you have for the electron, the uncertainty in the momentum and the uncertainty in the position multiplied together must be greater than a certain value. And that particular value is actually the reduced Planck's constant h bar divided by 2. Okay, so this again is something you can understand in terms of wavelets quite nicely. Imagine I want to have a wavelet which has a very small uncertainty in the position of the electron. That means I would take the envelope to be very sharp, something like this. So the phase in here would look something like this. Okay, so this wavelet here would have small uncertainty in the position, but because you only have about one wavelength of the wave in blue here, you therefore have a very large uncertainty in the momentum in the Fourier transform. On the other hand, if you want to have a low uncertainty in the momentum, then that means you want to have a wavelet which includes many wavelengths, like this. But that means that you will need to have a very long envelope like this. So a wavelet which looks like this will have a small uncertainty in the momentum, but it will have a large uncertainty in the position. Okay. And in both of these cases, what the Heisenberg Uncertainty Principle says, if you multiply together the uncertainties, then the product must be bigger than a certain number. Okay, so one thing we haven't talked about yet is how does the wave function behave as a function of time. And here I can't give you a precise answer, but there is an equation for it. Okay, so in quantum mechanics you will learn about something called the Schrodinger equation. Okay, and what is the Schrodinger equation? It's a differential equation. For the wave function axt. Okay, so by solving this differential equation, you can see how the wave function axt depends on the function of time. So I'm not going to give you the equation or talk about its solutions, but I am going to show you an animation of what this Schrodinger equation predicts for wavelets. So that is in the animation here. Okay, so before I start the animation, you see what you have here is a wavelet. Okay, so it has a well-defined localized position, and its momentum is related to the wavelength here of these red lines inside the wavelet. And this animation is just going to show you what the Schrodinger equation predicts for the motion of this wavelet as a function of time. So if I start, okay. Okay, so here you can see this has a momentum given by the wavelength here, which is in the positive x direction, and therefore as a function of time, as you would expect, the whole wavelet moves in the positive x direction. Okay. So the first thing this animation shows is that the wave, y, the wavelet is moving in this direction, and its motion, if I take, say, the center point of the wavelet here, its speed is simply given by its momentum divided by its mass, where its momentum is given by the wavelength. Sorry, I don't know why that keeps happening. Like this. Okay. The second thing you can see is that the wavelet does not stay the same width. If you look at the width of the wavelet, in other words the uncertainty in the position at the start, then as the wavelet evolves with time, you can see it's getting wider, right? Okay, it's getting wider and wider. Another thing you can see is if you look at the front end and the back end of the wavelet, then the wavelength is different. At the front end here, the wavelength is smaller, and at the back length here, the wavelength is longer. And that makes sense because a longer wavelength here corresponds to less momentum, so less velocity. So at the back end here, where the wavelet is moving less quickly, you have a longer wavelength. And at the front end, where the wavelet is moving faster, you have a shorter wavelength. Okay, so the wavelet as a function of time gets wider. Okay, and this is related to the uncertainty in the velocity of the particle, right? Because you don't know exactly what the velocity is, sometime later you have some uncertainty in its position which grows as a function of time. So the wavelet spreads out. Like I said, this is related to the uncertainty in velocity. Okay. Oops. Okay, so the next slide is showing two wavelets, and the first one here has a more well-defined position at the beginning, and the second one here has a less well-defined position. So if you wait until the animation runs around again, you can see that the wavelet at top is narrower than the wavelet at the bottom. So here we have a starting with a small uncertainty in the position, and here we start with a large, or at least larger, uncertainty in the position. And you can see as a consequence that this wavelet spreads out much faster. Okay. Later on in the evolution, this wavelet stays relatively narrow, whereas this one spreads out much quicker. Okay, and that's related to the uncertainty in the speed. Okay, so because this one starts with a small uncertainty in the position, this means it must have a large uncertainty in the momentum, and therefore, as a function of time, the uncertainty in position grows much faster. And conversely, this one starts with a reasonably large uncertainty in the position. It therefore can have less uncertainty in the momentum, and therefore the wavelet does not expand so quickly. Sorry, I don't know why that keeps happening. Right, okay, so these are exact solutions of the Schrodinger equation, which I haven't shown you about, but you can understand the picture just in terms of the de Broglie wavelength and the relationship with the momentum and therefore velocity of the particle, and the Heisenberg uncertainty relation, which tells you that the narrower the wavelet is to start with, that means less uncertainty in its position, that will give you more uncertainty in its velocity, and therefore the wavelet will expand much more rapidly as a function of time. Okay, so finally I want to use this to answer the question that was asked on the WSQ sheets last week, when can we treat a particle like a classical particle, and when do we have to treat it like a wave? Okay. And that basically depends upon the sort of length scales you're interested in. You can see that you can think about this wavelet as behaving just like a classical particle as long as you don't look too closely, right? So as long as the width of the wavelet stays less than the widths over which you are interested in your experiment, you can treat this just like a classical particle, right? Because it has a well-defined position, and that position just moves with a constant speed. Okay. So when can we treat electrons as classical particles? And the answer to this is you can do this if the spread of the wavelet which is the uncertainty delta x, is much less than the length scales of your experiment. Okay, so what are the length scales of the experiment? Well, in the two-slit experiment, you're interested in the width of the slits and the distance between the slits. Okay. So in other words, if I were to do the two-slit experiment like this, if it were possible for an electron wavelet to be localized enough in space so that by the time it went to the slits, it was definitely localized around one of the particular slits, and if the wavelet here was smaller than the slit width, then it would just continue through like a classical particle, and you would get a result exactly like you would for classical particles. Okay, but in fact, if you look at the uncertainty principle, which says this, h bar over 2 is of order 10 to the minus 34. Okay, we can write the uncertainty in momentum as equal to the uncertainty in the velocity times the mass, right? Because at least for the Newtonian case, p is just mv. So we can rewrite Heisenberg's uncertainty principle as uncertainty in position times uncertainty in velocity should be greater than h bar over 2m, and for the electron, m is about 10 to the minus 30 kilograms. So this gives you an uncertainty of 10 to the minus 4 in units of meters per second. And this is much too great, basically, because here the widths you're looking at are, for example, in the diffraction experiment, the widths in the atomic lattice, which are about 10 to the minus 10 meters. And if you want your wave function to be localized over that sort of width, 10 to the minus 10 meters, then the uncertainty in the velocity must be greater than 10 to the 6 meters per second, which is a huge uncertainty in the velocity, right? And what that means is if you start with an electron which is this localized, then the electron wave function is going to spread out incredibly rapidly. So by the time it reaches the slits, it will be covering both slits, so you can't say which slit the wave function has passed through, and again, as it passes through the slits, it will spread out again. So the wave functions from the two slits do overlap, and therefore you will get this interference pattern. Okay, right, so that is not a full answer, but hopefully that gives you some idea. When can you treat your electrons or your other particles like classical particles? And you can do this basically if it's possible to confine the wavelet so that it stays much smaller than the length scales of your experiment. But if you look at what the answers actually are for the electron, and say in the diffraction experiment here, that's totally impossible to do. Right? To have the electron localized well enough that you can say it's definitely going through the first slit or it's definitely going through the second slit, that would introduce a huge uncertainty in its velocity. Okay, so just before I finish this video, one final note. Here, because in terms of the uncertainty relationship for position and velocity, you have a 1 over m. This tells you that if you have a massive particle, you can control its position and velocity to a much lesser uncertainty. So what this means is that wavelets of more massive particles expand. Okay, remember the expansion of the wavelet is related to the uncertainty in the velocity, and therefore they expand more slowly. Okay, so if you were to compare, say, an electron with an atom, which is 10,000 times heavier, then you can localize a wavelet of an atom much better. Okay, so in other words, it will move and spread out much more slowly, and it's much easier to treat it like a classical particle. And this continues up to macroscopic scales. If you think about like a tennis ball, firstly, you never want to measure the position and velocity of this tennis ball with such a high accuracy. And secondly, because it has a large mass, really to treat it quantum mechanically, you should write down a wave function for this tennis ball, for this macroscopic object. But it's possible that this wave function as a wavelet just looks exactly like classical particle. Basically, the wavelet can be very well defined in terms of the position of the center of mass and in the velocity of the object. So you never have to consider these effects arising from the expanding of the wavelet or the interference patterns such as seen here. Okay. So although we think that the entire universe is described quantum mechanically in terms of these wave functions, if you consider something which is macroscopic, something you can see like a tennis ball, the uncertainties in the position and velocity are so small and remain so small that you can basically consider them just as a classical object with a well-defined position and momentum. But if you do this, the same thing for electrons, it doesn't work, okay? Because electrons have much less mass, and therefore the uncertainties in the position and velocity are much more significant. Okay, right, so in this video then we've talked about the connection of the wave function to how you measure the position and the velocity of particles. This leads to the Heisenberg Uncertainty Principle, which says that you can never measure both position and velocity to greater than a certain value of uncertainty. So there's a limit to how precise your measurements of position and velocity can be simultaneously. And finally we've seen how this relates to the evolution of the wave function and when you can treat quantum particles just like classical particles, based upon the localization of these wavelets. Okay, so that's the end of this video, and this is the end of the section of the lectures on quantum mechanics. So because I haven't really been able to introduce the mathematical theory of quantum mechanics here, a lot of these ideas are not totally well defined, so I wouldn't worry too much if you're confused about them still. But if you take a quantum mechanics class, then all of these ideas you will see again from the point of view of this mathematical theory defined by the Schrodinger equation.